În această seară, profesorul Albert LÁSZLÓ BARABÁSI, ne propune un subiect actual și captivant, formula o știință a succesului. Îi mulțumesc profesorului BARABÁSI pentru că ne îndeamnă să schimbăm din temelii felul în care înțelegem succesul, iar celor care ne stați alături vă doresc o seară inspirată. Semnează Maestatea sa Margareta Custodului Coroanei României. Cu aceasta intervenția mea se termină. O să rog pe domnul Andrei Dorobanțu, părintele acestui proiect, să preia conducerea conferinței de astăzi.
Doamnelor și domnilor, vi-l ofer acum pe profesorul Albert LÁSZLÓ BARABÁSI.
Îmi pare rău că nu pot să predau în românește, că româna mea este foarte ruginită. N-am apucat să vorbesc românește de mai mult de 20 de ani, așa că va trebui să mă scuzați că o să trec pe engleză. So, once again, it's a real pleasure to be with you. And Andre and I had kind of talked a little bit about what should be the subject of today's discussion or today's lecture. And we decided that it was best to actually talk about a subject that is close to all of our heart, which is success. That is, how does success emerge in life? How does it emerge in science? So my goal, let me kind of share my screen. And my goal is to really kind of tell you about the research that my lab has done in that space. And of course, you know, success is something that that has so many different meanings. So therefore, the first question that we need to ask here is, you know, how do we arrive to success? How does a scientist, how does a physicist arrive to kind of explore the patterns and the laws of success? And to understand that, I should kind of step back and indeed kind of talk about the fact that I'm a physicist by training, but I continue to be a physicist at heart, and I continue to be a physicist in terms of my tools and my thinking about the world. However, I use that type of training to take physics and physical thinking in new directions. And kind of about 25 years ago, I started to use statistical physics to explore complex networks. Why networks? Because our world is dominated by really complex systems, complex networks. And one example is you see here, what you see here is nothing but the structure of the internet. It's an archetypical example of a communication network where computers are connected by various cables. And this is the network through which I can actually give this lecture today, despite the fact of not being able to kind of be in person in Bucharest. But we have just as important networks within ourselves. So what you see here is nothing but the protein-protein interaction network between the human cell, and I could play it again, which is kind of telling us how the different proteins in the cell are connected to each other and how they lead to disease and health problems. And of course, we are part of networks when we work in an organization or in a company. So what you see here is nothing but the employees of a company that are connected based on the fact of how often they talk to each other, how often they communicate with each other, how they turn to each other for advice, and so on. So, and the last kind of 20 years in my lab has focused entirely on the laws that govern the emergence of these very complicated networks, from communication networks to biological networks, social networks, as well as developing the tool set to quantify their emergence as well as their structure. And as a result of that, a new field of science has emerged that we call network science today. But as we were studying networks, I was always struck with the following question. It's one thing to understand how a network emerges and the large-scale structure of these networks. But what about the node, which is you and I are nodes in this network? How does the network affect our ability to do things in the world that we exist in? How do these networks affect our success? And this line of research, which we often call in the lab the science of success or science of science, is really kind of driven by the realization that we are not independent of each other, and we're embedded in networks that affect our ability to achieve certain things in life or in profession. And so we said, well, now that we know these networks, particularly in science, could we tell how these networks affect me? And it was this question that drove us to the question of success. And as we kind of started to explore success from a quantitative perspective, we realized that we must actually carefully distinguish two very different things that are often used interchangeably, more like synonyms of each other: the notion of performance and the notion of success and recognition. And the way to think about it is performance is what you do, how fast you run, what kind of paintings you paint, what kind of radio show you run, whatever you do, how well you cure your patients, whatever you do, performance is what is that really that kind of deeply linked to your actions. However, success is really about what does the community notices from that, whether they notice your performance, whether they appreciate it, and finally, whether they recognize it and award you or reward you for that. So in other terms, performance and success are very different animals, because performance is about you, but your success is about us. It's about us as a community. And we have to make that distinction very carefully as we move forward. This doesn't mean that you cannot have a sense of individual success. You know, you could consider a success that you got up early in the morning and you achieved something. You could consider personal success of how your peers are doing or how you achieve certain tasks and so on. And that is very important, but that is really a component of performance, right? Those type of sense of personal success affects your ability to do things. When we talk about success, we think of success as being a collective measure, something that the community gives to you. And that's what we would like to quantify. Now, let me give you an example to really understand the difference between performance and success. So let's take a tennis player, Novak Djokovic, for many years the #1 player out there. And when we talk about his success, we can use many, many numbers to really reflect on that. We can say how many millions of hits he has if you do a Google search after his name. You can talk about what is his ranking in tennis, how many score points he has in tennis, how many wins and losses he had, how many people visited his Wikipedia page, say, last year, how much money did he win, and how much money did he earn from endorsements. But when you look at all of these numbers that all kind of reflect on Djokovic's success, if you look more carefully, you realize that these numbers really mix performance and success. Because some of these numbers are truly performance numbers. How many games did he win and lose? That's really about him as an individual and his ability to play tennis. The score points simply follow his wins and losses, so that's a performance measure. His ranking is also driven by his ability to play tennis and how well he plays. That's again a performance, and so does his winnings. But when it comes to how many people look at his Wikipedia page, how many people Google him on a daily basis, and how much money did he get in endorsement, those are things that we as a community give it to him. We search for him, we visit his Wikipedia page. Our money goes to them as endorsement by buying the products that he actually endorses. So these are not performance measures, but they are really success collective measures. Now, of course, the reason we give them so much money in the endorsement is because he has performance, which kind of leads to the idea that obviously performance and success are not independent of each other. You must have performance in order to have success. But we were curious, is that relationship is so strong? Because we always know in our environment individuals who are very successful, yet we do not perceive that they would have the performance that would go with that success. So does really performance drive success? So we set out to measure that and to analyze that, the data, to see whether that connection is there. And the way we did that is we said, this is how many of us are visiting every day his Wikipedia page. That's what you see on this particular screen. And what we were curious is whether we could actually predict this. So what does this curve show? That, you know, at the early stage of his career, we were not particularly curious about him, right? Not too many visits he had on his Wikipedia page. When he started winning seriously, more and more people showed up on his Wikipedia page. And these peaks obviously corresponds to moments when he had major wins or major losses against very important tennis players. And so then we were all curious about him and we flocked to his Wikipedia page. So the question would be that obviously this is a success measure because it's not something he does. We do it to him, right? We go and visit his Wikipedia page. Well, could we predict these curves from performance only? And in order to do that, we ended up actually building what else but a formula. And that formula is what you see over here. And what is special about this formula is that on the left-hand side, what you see is the predicted number of Wikipedia page views. So this is what we're trying to predict. How many of you and us will actually show up on the Wikipedia page tomorrow? What you have on the right-hand side, from which we're predicting, is something, the only link to his performance. That is, all of these variables connect to whether he played in that moment, what was the level of the game he played, that was it an important championship or not so important tournament, what was the level of the opponent that he had in that particular made, and did he win or lose? So all of these variables are connected to his performance. And the question we ask, just knowing his performance, could we accurately predict his, our curiosity about him? So let me show you what this formula predicts. And that's the red line, right? And what you see that it does a pretty good job. It temporarily captures the moment when we become very interested in him. These are typically the tournament times when he wins or loses, and also almost captures the magnitude of the interest as well. And so the fact that the red and the blue curves are so overlapping has a very important message to us, because it tells us that performance drives success. That is, that when he performs well, or he performs in a visible way, he also gets our admiration or our interest, at least, in him. And this is obviously good news, because it's confirming what our teachers and our coaches told us day by day, that you need to have performance, you need to study, you need to run, you need to exercise, you need to do all of those things so that you will have performance, because you must have that performance to get to the success. So far, so good. But when you're a scientist, you also start looking and say, how well does it predict? And what's the difference between performance and success? So that's what I'm going to actually go ahead and talk to you about next. And I'm going to make a very unexpected statement, which may not be so unexpected right away, because we have to unpack it. What I'm going to try to convince you is that performance and success are mathematically very, very different objects. And the way we say it is that performance is bounded and success is unbounded. And that has very important implication of how success emerges. So what does this mean? What do these statements mean? Well, to understand that, let's start with the fastest man on earth, right? So this is, everybody recognizes him as being Usain Bolt. And what he's famous for is that he wins most of the competitions that he actually enters. He is literally the fastest man on earth when it comes to how fast he runs. But what is amazing about him is that, you know, he's not so much faster than his competitors. Not only that he's not so much faster, but when he wins, he's not running twice as fast than his competitors. Less than 1%. That is, the amazing about him is not that he's such an outlier when it comes to how fast he runs, but he's just barely running faster than his competition. And the fact that he can only beat by less than 1% his competition indicates a very important thing about our performance, about your performance and my performance, is that our performance is bounded. That he may be the fastest person on earth, and I may be one of the runners, the slowest runners out there, but still he doesn't run 10 times faster than I do, right? He does run twice as faster, maybe 50% faster than I do, and that's enough to win all the competitions and for me to win no competition that I would enter. But the difference between he and I is relatively minor when it comes to the absolute measures. And it's not only about running, right? Not only about Usain Bolt. What turns out that in no matter what area we look at it, and here I'm showing you actually at the time that takes for his competition to really run 100 meters, and you see how close they are to each other. And one wonderful manifestation of that tiny differences in performance was actually, we saw at the last Olympics that we had, where I'm giving this talk right now from Budapest. I couldn't fly to Boston. I had to kind of speak from here. And of course, that the last Olympics in Rio, we had this funny situation that the top swimmer from Hungary, Cseh, has actually had to share the prize with Phelps and Lacrosse. That is, 3 individuals have shared the same position on the podium. And the question is, why is that? Is it because we didn't know who arrived faster? And no, there was no ambiguity. There was a clear video showing which of the 3 swimmers had touched the wall first. But yet, we don't know who is swimming faster. And the reason we don't know who is swimming faster is because the swimming pools are only measured with 2.5 centimeter accuracy. And the time difference between the 3 swimmers was less than it takes for swimming that 2.5 centimeters. Hence, the Olympic Committee could not decide, given the uncertainty of the size of the swimming pool, who is the faster winner. They knew who arrived first, but they didn't translate into the faster winner. Now, I love to show this example because it kind of indicates that how bounded performance is. That if not even in the sports, where you have chronometers and videos tracing us, you can really see who is the faster. Now think about it, what happens to professors where we don't have chronometers and we do not have videos to watch us? How do you know who is the better teacher? How do you know who is the better scientist? Who is the better doctor when you don't have these precise tools by which we measure the differences? And the answer is you often don't, right? You can distinguish a good doctor from a bad one, a good teacher from a bad one, but you can never distinguish two good teachers from each other or 2 good doctors from each other, because performance is bounded. And at the top, the difference in the performance is almost impossible to measure. Those of you who are more mathematically minded, a bounded performance means that it typically follows an exponential or Gauss-like distribution. But why performance is bounded, success is not. And let me tell you what I mean by that. So this is actually a short part of the bestseller list in the New York Times in October 4, 2009. This has been more than a decade ago, and the date yet nevertheless has a significance for me, because that was the year that I released my second general audience book called Burst, the one that is unfortunately not yet available in Romanian. Linked, the first book, and the formula, the third, are already available, luckily. And when that book came out, I was in New York with my publisher, and we were curious who is on the bestseller list, that who is effectively our competition, right? And then we realized that there were 2 books on the bestseller list. If that was the week when Dan Brown's famous book, The Lost Symbol, came out, and also this kind of the week that The Last Song came out by Nicholas Sparks, and he's a very well-known American writer and very, very popular. And when you look at the bestseller list, Dan Brown was number 1 and Nicholas Sparks was number 2. And just looking at it, you would say, well, if Dan Brown, if the Nicholas Sparks publisher would work a little harder, there should be no problem. He could be number one. He could easily unset Dan Brown. Well, it seems to be if we just simply look at 1, 2, 3. It's a very different story if we look at the precise measure, the success measure based on which one this one is based on. Because when it comes to books, the one success measure is really the number of copies you sell. So let's see what happens with Nicholas Sparks, right? Nicholas Sparks' book came out in October, as I said, and in the first week sold more than 100,000 copies. This is an amazing number. Typically, you become number one on the New York Times bestseller list by selling anywhere between 20 to 30,000 copies that week. So Nicholas Sparks has overcome the necessary number with about a factor of 2 to 3. So he should be number one, but he isn't. Why? Because the same week came out Dan Brown, and he didn't sell a little more than 100,000 copies, but that week he sold 1.2 million copies of his book. And this is when I say that success is unbounded. That why, when it comes to performance, the difference is tiny between the number one and number two, less than 1%. When it comes to success, the difference can be orders of magnitude. And here we see a factor of 2 different, or factor of 10 difference between them. And that's because success is a collective measure. It's all of us who are buying the Dan Brown book, right? And it's not limited by Dan Brown's performance. It's limited by our attention span and our interest with them, and therefore his skills. And hence the differences between number one and number two when it comes to success measures, that is how much we appreciate his books, can be orders of magnitude and not just 1%. So this is where it kind of comes to this conclusion that performance is bounded. No matter how good you are, you need to realize that you are not much better than another person who's just as good at their profession. And even if you are better than them, no one will know that because it's impossible to measure the performance differences at the top. But we can easily measure the success differences because success differences are unbounded. And the most successful person can be 10, 100, and often 1,000 times more successful than the number two. Now, this is, of course, a very interesting dichotomy. How does this giant difference in success emerge between people whose performance is indistinguishable? And unfortunately, we will not be able to go into this lecture. If those of you are interested in this topic, in my book, The Formula, which just came out in Romanian, I devote 2 chapters to that very question. What I would like to do today, now, is to kind of switch gears and talk about when does success emerge in an individual's career? And how do you look at the individual's career from the perspective of success and performance? How do we apply these ideas to one particular individual? And I'm going to start with an individual that I know very well, kind of the best I know, which is myself, right? And what I'm showing you here is really my own scientific career. What does this mean? Horizontally, you have the years. From my very first publication and my first 2 publications that was co-authored by myself and Andrei Dorobanțu, and that I wrote actually while I was a student, an undergraduate student in Bucharest, all the way to the papers that I published kind of last year. So that's what you have on the horizontal axis. Every paper, every research paper that I publish as a scientist is one circle. However, what you have on the vertical axis is something that we in science use as a measure of success, which is how many people have cited that paper. That is the number of citations. And why is that important? Because the more people cite a paper, that means that the larger community is interested in your work and kind of reflects how much impact you have on the scientific community. And what you see on this curve is that I was very, very busy for the first 10, 15 years of my career without much success. That is, I wrote lots of papers, but really the community wasn't paying much attention. So this was that part of my career, the first 10 years, running fast, not getting anywhere with it. My enthusiasm was unwavering. I kept writing more and more papers, but then kind of there came this moment around 99 or 2000 when I chose to change topics, and I became suddenly interested in networks, and I started publishing in networks. And suddenly, after that transition, I published one high impact paper after the other one. And what you see here is not the total number of citations. This is what we call the citations within 10 years. For technical reasons, that's all we show. And these papers today have more than 30,000 citations, if you count the total one. But you see that then came this period of my life where I would publish one high impact paper after the other one, and it felt really good. It felt nothing could really go wrong in my career. But then the next question, the final question comes, what happens here, right? And here we don't know what happens because not enough time has passed. The decade hasn't passed for these papers to acquire the citations that they may actually kind of capture over time. So given that, we don't know what's the real impact on the community. But is it possible that I lost that, right? Is it possible that I entered a new phase of my life, which is something like that, right? So how do we know that? How do we quantify that? And one way to look at it is that what was the time in my career when I published my highest impact paper? And in this case, in my career, that was the 63rd paper that I ever published, and it came about 13 years within my career. This is what we call typically the academic lifetime or academic age of a person, right? Because your academic age starts when you publish your first paper, like the paper Andrei Dorobantsyn I published back in 1989, and then it clicks further with every single paper. And the question was, when that moment comes? Well, I was particularly curious about that because I was wondering whether we could tell from the history of the publications of a scientist when that moment comes, or if that moment comes. So therefore, we ended up kind of taking for each scientist and identified that moment of success, the moment when they published the highest impact paper, whether it was a Nobel Prize discovery or whether it was a paper of really weak impact. But what was special about that it was the highest impact paper in that particular scientist's career. So we took actually tens of thousands of scientists whose career we reconstructed, and then we asked for each of them, how many years did it take to get to that moment? And then we were curious if we could actually predict that moment coming. So here I'm going to show you a plot that will look at performance. That is, how many papers does a scientist publish as it comes to that critical moment when he publishes his or her highest impact work. So the highest impact work will be always here, and then we see how we're approaching it. And what you see that in terms of the number of publications per year, they start growing almost linearly as we're getting to that moment when that scientist publishes his or her highest impact paper. So really, in terms of performance, we can see that the scientist is working more and more and more, trying to reach that moment of success. And interestingly, after that moment comes, they publish their highest impact work, even though they don't know that's their highest impact work, because it could come an even higher one later in their career. Somehow their performance kind of saturates, as if they would realize that this is it, now I arrived. But this is performance, right? How hard we work, how fast we run, how much we publish. But how about success? Could we also see in terms of the impact of the papers that they're really getting higher impact until that magic moment comes? So here I'm going to show you the number of citations each of these papers gets as we're getting closer and closer. And this is the critical moment when that highest impact paper comes out. And we find a curve like that. And unfortunately, this is a very odd curve because it's totally flat. Then there is this big discovery and then flat after that. What does this really mean? Well, this we actually call the finger curve, because what it tells us is that we can't see success coming, nor do we learn from it. That is somehow the papers that we published before our biggest discovery, they don't seem to have an increasing impact. It's not that we're getting better and better, but suddenly in our career, unexpectedly that high impact paper comes. And then it's not followed by necessarily by other high impact papers, sometimes done, but typically doesn't. So it's really a singularity within our career. But now the question is, when does this moment happen in a scientist's career? And we have lots of interesting hypotheses about that. And what I mean by that is really, you know, Einstein kind of said once is that a person who has not made his great contribution to science before the age of 30 will never do so. What does he mean? Well, what he really means is reflecting a belief that was very strongly there and still there in science, that you have to be young to make a big discovery. Why did Einstein say that? Because he looked around at his peers, the people who created quantum mechanics, and he realized that Heisenberg was 24, Dirac was 24, Pauli was 25, Farber was 25, and so on. All of the people that he admired, most of them were really in their 20s or maybe early 30s. And there was only one old guy, quoting old, right? Planck, who came really late to his career, to quantum mechanics, and he was 42, but he was still a relatively young person. So this kind of observation has really started a thinking that creativity really belongs to young people, and you need to be young to make a major discovery. Is this so? Or is this something that is only true for Nobel Prize winners, and maybe it's not true for the rest of us ordinary scientists? So we went out to check that. And the way we did that is, again, we kind of identified for every single scientist how many years into their career have published their highest impact paper. And what you see here, each line corresponds to a career of a different scientist. So one line is one scientist from their first paper to the last one. And you have a red dot when that particular scientist publishes his or her highest impact publication. That is their career best. And these are all close career. These are all careers of scientists who have retired from science, so we can make that assessment. And when you look at this curve, these red dots seem to be all over the map, right? So they seem to be everywhere, not only in the young age, right? But we need to kind of quantify that. And the way we can actually quantify that is to ask the question, what's the probability that you publish your highest impact paper, say, within the first year of career, or maybe 3 years or 10 years into your career, or 20 years into your career? So this is your academic age, not your year age. And oops. And what you see here is the fact that the probability to publish your highest impact work really kind of flat for the first 10, 20 years of your career. And then it starts to drop very, very fast. Now, at first, this is actually kind of indicating that Einstein and his colleagues were right? That because if you take at face value the work, it looks like that your chances of really making a big discovery, say 30 years into your career where I am, is less than 1% compared to what you do in the first 20 years of your career. So really you have to be in the early stage of your career to make the big discovery. But this is not so simple, actually, because it first would indicate that I'm already in that stage of my career, but to really understand the answer, we need to kind of look more carefully at the data, because we need to ask, what happens if I randomize the people's career? What happens if success is totally random in the career of a person? And the way we tested that is that we took each person's career and we ended up swapping the impact of the papers among all the papers they published. So they keep the timing of the publication, we kept the number of publications, but we swapped the impact. And this is what we call the randomized curve. And the randomized curve is undistinguishable from the real curve. And the randomized curve is nothing but the productivity here, because it just tells you what's the likelihood that you will publish a paper in this year. And what you see is that productivity is indistinguishable from success. In other terms, what you see is that really, when it comes to if I just put from the first paper to the last paper in an order, you have equal chance for your best paper to be the first or the second or the third or the last in your career. That is, when it comes to success, you never really know when your hit comes. It could be with the same probability your first or the last or the middle paper of your career. So in the space of the projects that you do, success is totally random. And this is not only true, by the way, for science. It's true in many, many other careers. You don't know as a painter whether your first or your last paintings will be the most valuable or the one that will bring you to success, or the mid-career paintings. And even as a businessman, sometimes success comes very late in life and not early on, despite the belief that in the business also you need to be young to be successful. And let me show an example to indicate that. So what you see here is Frank Wilczek, who got the Physics Nobel Prize in 2004 for the very, very first paper that he wrote ever in his career. He was a graduate student, and the first publication was the one that 40 years later gave him the Nobel Prize. But my favorite is not Frank Wilczek, but John Flynn. John Flynn was a chemist who kind of spent the last 15 years career before retirement at Yale University. And the only reason he actually retired is because Yale University forcefully sent him into retirement when he reached retirement age. Back then in the US, there was a mandatory retirement age, as there is one in Europe as well now. Now there is none. So effectively, Yale decided to close down his research lab and effectively let him go. But he was a person with dreams. And instead of really abandoning science and retiring, after retirement, he ended up joining another university, the Virginia Commonwealth University. And he was there where he published a paper on electrospray ionization, for which 15 years later, way above beyond 80, got the Nobel Prize for chemistry. So John Flynn is the example that creativity doesn't fade with time. Productivity does. So the way to interpret the curve that I showed you earlier, that it's not that scientists are less creative later in their career, but they are less likely to try again. And as long as you keep your productivity up, success is totally random, could come at any age. And the reason why we often perceive that elderly people may not be as creative is not because their brain is not creative, but because for whatever reason, they stop trying to be creative. They stop trying to put projects out, to publish papers, to paint paintings, to solve interesting problems, and so on. So one kind of important message for me, that as long as I keep going, I still have a chance to publish things that could overcome anything that I did so far in my life or in my career. Now, the last topic that I would like to kind of talk to you about is, let's assume that that big discovery happened. Who is going to get the credit for it, right? You made the big discovery, you painted that painting, you put together that business. Who will walk away from the credit? And sometimes it's easy to know that, right? So when Einstein published in 1905 his relativity theory, he was the only author in the paper. There was no ambiguity who should get the credit for the discovery, because only his name was on the paper. Same for Darwin. When he published his theory of evolution, he was the sole author of the book in which he released that. But today we live in a different world where no discovery can be made alone. We need to work together. We need to collaborate with colleagues. We need to pull our resources together to make discoveries. So a paper today looks like that. This is a Nobel Prize winning paper. Whom do you think should get the Nobel Prize? How do you decide? Obviously, these two gentlemen, right? So the question is, how is credit assigned to any achievement when the work is not done by an individual, but is done by 175 individuals, as you see in this particular image? So nevertheless, it is assigned, right? Because the Nobel Prize Committee decided that for this major achievement that include hundreds of researchers actively, you know, only 2 individuals should be given the recognition of a Nobel Prize. Well, in order to find that, we ended up building a formula that measures the amount of credit a scientist gets when it comes to a particular publication. How do we do that? Let me give you a hint of what's the idea behind that. So here is a paper, a Nobel Prize winning paper by 2 authors, Baba and Nagishi. And this paper, as I said, has received the 2010 Nobel Prize in Chemistry. And what is interesting about it is that if we look at what are the most co-cited paper with this paper, that or the community cites it together with us, and we rank them, what are the 5 most co-cited papers, it turns out that they're all papers by Nagishi, and Baba is always missing. So that indicates to us that really that Nobel Prize discovery was really the work of Nagishi, and Baba was there to help as a student, as a collaborator, but he was not part of the discovery journey because Nagishi had published multiple papers preceding and following particularly this discovery, where he pulled the story out in a way that it was worth a Nobel Prize, and Baba was not there. So, however, and not surprisingly, it's only Nagishi who got the Nobel Prize in this case. Let's look at a different case. 2010, again 2000 year Nobel Prize in physics now. And what's interesting is that this was shared by LÁSZLÓ and Gain, and when we look at the 10 most co-cited papers on this discovery, always LÁSZLÓ and Gain are together in different orders, sometimes first, sometimes last author, but they're always together. So from a scientific perspective, they're indistinguishable. And not surprisingly, the Nobel Prize Committee decided that both of them preserve the Nobel Prize, even though one was an older, more like an advisor, and one was a younger individual, more like a student or the postdoc in the lab, right? So could we quantify that? And in order to do that, we built, as I said, a formula that looks at a particular paper and looks at who cites that paper and who are the co-cited paper, what other papers by the same authors are co-cited. And we try to kind of figure out, the formula simply asks to what degree the red or the green authors' papers are co-cited with the discovery that we're interested in that. That is, in the mind of the community, the work of that author is connected to the final discovery. And at the end, we get a credit share, a number saying what percentage of the credit goes to the red and what percentage of the credit goes to the green paper, a green author. In this case, you see, the algorithm decided that the red author gets more credit than the green, because several of the red authors' papers were co-cited with this paper, and only on one of them was the green present. So we applied this algorithm to the problem that we had before, and the algorithm decided that 72% of the credit should go to Nagishi, and Baba should get only 28%. Hence, the prize went to Nagishi. But in this case, the algorithm said half and half, and hence the prize was shared. Now, how do we know that this formula is right? Because I may have just picked the right example. Well, we need to test it. We're scientists. So we ended up applying this formula to all the Nobel Prizes in physics and in chemistry. And here what you see is that each year the Nobel Prize was given, and the number of authors in the papers that the prize was given. And the list starts in the kind of 1995, because that was the first year when the Nobel Prize Committee started to officially announce not only the prize winner, but also the research paper for which they awarded the prize for. So we know what paper got it. And then often that paper, sometimes the paper had only a single author like here, but sometimes had many, many authors like here in 1995, or 5 authors. And then the authors, some of them got Nobel Prize and some of them didn't. And we put a red dot when our formula has correctly predicted who should be the Nobel Prize winner. And we have an empty dot when we didn't pick it and there was no prize either. And we give ourselves a black dot that you remember from kindergarten, maybe some of you. I certainly don't remember in Romania getting black dots in kindergarten when I did something wrong, when the algorithm has mispredicted. It wrongly predicted who should get the Nobel Prize. And you see, we have mostly red dots. We hardly have any black dots because most of the time we got it right. Every time we missed, there was a juicy story behind that. And it turned out it wasn't the missing of the algorithm. It was often a failure of the committee as well as the community to recognize the right person for the prize. Let me tell you one story that is particularly heartbreaking and very enlightening to me. And for that, we're going to look at the 2008 Nobel Prize that was given to 3 individuals for 3 different papers. And you see, we claim that one person should have gotten who has not gotten it. Well, why did we do that? What was the Nobel Prize for? This was a Nobel Prize that was a no-brainer Nobel Prize in the sense that somebody needs to receive a Nobel Prize. And this was the so-called GFP or green fluorescence protein. Those of you who occasionally see these biological cell cultures where different cell types are lit up and different genes are kind of fluorescent in fabulous colors, those colors are possible because of the GFP molecule. What these scientists have done is that they realized that there is a jellyfish has a particular protein that is fluorescent, and you can take that out from the jellyfish and put it into other cells, and you can use as a lamp within the cell. And the Nobel Prize for that discovery came for Shimomura, Shalfi, and Sien, who are shown over here. And oddly enough, our algorithm insisted that the prize should primarily go to another individual whose name is Douglas Fraser. Now, fine, there may be a dispute, but here was what was odd about Douglas Fraser. We could not find him anywhere within the scientific community. Yes, he did publish some papers kind of 15 years earlier that were in the GFP era, but he was nowhere to find. We couldn't find him in a university. We couldn't find him in a research institution. And he hasn't published any papers for many, many years. Eventually, we managed to track him down. He was in Missouri working as a bus driver. To be more precise, he was working at the car dealership, and he would be the person who would drive you home from the dealership if you took your car in and you didn't have a car to go home, and he would come to pick you up and bring you to the dealership once your car got fixed. He was a car driver. Now, why would our algorithm insist that a van driver should get the Nobel Prize for chemistry? Well, the story goes like this. Douglas Fraser once was a young and talented scientist who was working at Bar Harbor, very elite research institution as a young faculty. And he was the person who first had the idea at the early ages of genetics that the reason why the jellyfish is fluorescent, what he's holding in his hand, perhaps could be traced down to one particular gene or one particular protein. So he ended up collecting a giant number of jellyfish and doing a giant number of experiments to identify which is the gene and which is the protein that is responsible for this fluorescent property. And he found that. He found that protein and ended up publishing in that discovery. Why was he curious? Because he knew very well that if there's a single protein responsible for the fluorescence, then he can take this protein out of the jellyfish and place it into other cells and use it as a light bulb that is active within the cell. And so after he identified the gene and published that, he wrote a grant proposal to the agency that funded him to do just that, to do the final experiment to show that he can actually place this protein into another cell. Unfortunately, his proposal got turned down. And what was different from him and many other scientists who carry on despite failures, he decided that he will give up science. He was so disappointed about the fact that he didn't get the money to continue his research that he shut down the lab and left the research, institution and moved on first to applied research. And then he lost that job and went to yet another company and lost even that. And then eventually ended up being a car driver. But there's a funny thing he did before he left, he closed his lab. He said, you know, I worked so long on kind of identifying this protein and no one seems to care. But there were two people that really cared about it. And he ended up, before he closed his lab, putting the protein or the gene, actually, the isolated gene, into a tube and mailing it to the two people who showed any interest in his research. He just put them in an envelope and sent these two envelopes out to the two individuals. Who were the people he sent this research, the gene to? They were Martin Chalfie and Roger Tsien. And Chalfie and Tsien had done what he was dreaming to do. They ended up putting actually that protein into other cells and showing its relevance and bringing him actually to turn into a very successful tool. So when it came to finally getting the Nobel Prize committee and the community looked around and there was no Douglas Fraser to be found anywhere. He was not part any longer of the network, right? Because he was not publishing, no one knew what happened to him, for all practical purposes disappeared. So the scientific community, the network of scientists have not activated and no one really proposed him for the Nobel Prize. They proposed for the Nobel Prize the people they knew, the people within their network, which is Martin Chalfie, Roger Tsien, and Shimomura, who came later in. So, and therefore the prize went to them. And this is very important because it shows this and the previous data that I showed you, that credit is very much based on perception, not only on performance. That is, you know, is like, how does the community view your work is how we actually assign credit. And here was a typical case of failure to attribute credit to the person who made the discovery. And to be honest, you know, when we come back to them, Martin Chalfie and Roger Tsien were very correct. When the Nobel Prize was announced, Tsien has actually given the first interview and he said, in my mind, the Nobel Prize committee has made a mistake. And the real winner of this Nobel Prize should not be him, but it should be Douglas Fraser. And he went as far actually inviting Fraser to the Nobel Prize ceremony. And it was that moment when actually Douglas Fraser gave an interview saying that in the last 5 years, this was the first vacation he as his wife were able to take together. Why is this important for many of you who are young people and kind of perhaps starting a career either in science or not? Is because it's not enough to have performance in life. You need to also force your community to acknowledge that. And you need to work hard to achieve the credit for that. When a young person joins my research lab in Boston, and we publish the first paper together, I tell them, congratulations. You now have a publication with me, perhaps in a great place, something that could start your career. But what you have to keep in mind, that this at this moment is my paper, not yours. Because everybody knows me, they don't know you yet, and therefore they will attribute the paper to me and not to you. So your job as a young person now is to take that discovery and go out in the community and show them who you are and convince them that this is your work. That is, go out and fight for the credit that you receive. Because really, despite of what many people really believe in both in science and arts and other profession, that performance is necessary for success, but is not enough. And this may be a good point for me to close this lecture. And if there's one message that you want to kind of go away from that for me was a very humbling message, is that while performance is about you, your success is about us. And therefore, your community has a responsibility to nurture not only your performance and your ability to do things, but also to nurture your success. And this may be a good moment for me to stop. If you're interested further in this topic, I'm very delighted that this book is available in Romanian and you can read much more details about that. And I'm happy to stop and take any questions that you may have. Thank you very much. Mulțumesc foarte mult and mi face foarte multă plăcere că am avut această ocazie ca să predau pentru voi.